We have a compound P with the molecular formula C5H10O in this question, and we are supposed to find how many isomeric structure does P have, and we should consider structural isomerism and also stereoisomerism. Structural isomerism is actually the most common one. That means you change the skeleton of the backbone of the compounds. Stereoisomerism involves cis-trans isomerism or optical isomerism. So if there's a C-C double bond in the compound, then this compound might show cis-trans isomerism. And if you have a chiral center, chirocarbon in a compound, then it will have optical isomers. Okay. Now, this question also tells us that P produces orange precipitate with 2,4-DNPH. So this one tells us that P is a carbonyl compound. So P can be a ketone or an aldehyde with the functional group C double bond O, right? For aldehyde is C double bond OH. The functional group is at the end of the compound, the chain. Ketone will be a C double bond O bonded to two R groups, left and right. Okay. Now, I always prefer to start with structural isomers because I can just draw the display formula or structural formula to show the structure of the compound. So I'll start with aldehyde because I think it's easier. The CHO, the functional group C double bond O at the terminal. So I'll just write CHO at the end. Okay, left hand side. Okay, I've used one carbon for the CHO. That means I have another 4 carbon. I always start with the straight chain isomer because it is easier. Then I have the CH2. So this will be our first structural isomer. And I'll start playing with, putting branches on different carbon. So let's start with CHO again. That's a functional group aldehyde. Then go to the left, 1 carbon. So what if this carbon has 1 branch? Okay, that means I have 2 more carbon to the left. So there will be CH3, CH2, and then I put a H here. So that would be my second structural isomer. Okay, they are obviously different, so they are isomers of each other. So I believe there are more isomers for aldehyde. Okay, now let's say I put this one as CH2 now, and I put a branch to the second carbon next to the CHO. So I have 1, 2, 3, okay, 1 more. Okay. So these are 3 different structural isomers. Right, let's write more. Okay, what if this time this C is bonded to 3 CH3? Still 4 carbon, right? Of course, not including this one because the formula is C5. So 1, 2, 3, 4, 5. Okay, so for now I've found like 4 structural isomers, and I think I will not be able to write more for aldehyde. Okay, I'll move on to ketone. So ketone means the C double bond O is in the middle of the chain. Okay, so on the right hand side of this C double bond O cannot be H, left hand side cannot be H. If not, it will be an aldehyde. So let's start with CH3. So 2 carbon, that means 3 more carbon. Like what I said, I always prefer to start with straight chain carbon. So this is the first ketone. Second ketone, I start with C double bond O. Maybe this time I have 2 carbon on the right hand side. That means 2 more carbon on the right hand side. left hand side, 2 on the left, 2 on the right. Okay, altogether 5 carbon. Now this is the second ketone. I feel that this part is quite long. Probably I can put this CH3 to be a branch. C double bond O. So I put CH3 here. Because it's ketone, right? I cannot put H here, so I have to put CH3 on one of the sides of this C double bond O, so that it can be a ketone. Okay, right, CH3, 1, 2, 3, 4. Okay, I have one more. There will be CH3, H. Now I don't have enough carbon atoms to play with, to put another CH3 here, right? So that means I can only get 3 structural isomers of ketone for the C5H10O. Now, I think I'm done with all the structural isomers of compound P. Now, I can start considering stereoisomerism. Now, if you can see that all these ketone or aldehyde P, there isn't any carbon-carbon double bond in the structure. So that means none of these isomers will show cis-trans isomerism. Then we have to consider the second one. Okay, can we find any chiral carbon in any of these compounds? Let's look at the first one. Now, of course, obviously, all the carbons are bonded to more than one hydrogen. Chiral carbon must be a carbon atom that is bonded to 4 different groups of atoms. Okay, and this CHO, right? Because of this double bond here, is bonded to only 3 groups of atoms, so it cannot be a chiral carbon. No chiral center in the first isomer. Now let's look at the second one. Is there a chiral carbon? Okay, start from the left. No, not chiral carbon. Second one, not chiral carbon. The third one is bonded to CH3, bonded to CH3, CH2, ethyl group, bonded to hydrogen, bonded to CHO. Yeah, 4 groups of different atoms. Okay, so it is a chiral center. So this isomer number 2 will have an optical isomer. Okay, how do you draw the structure of this optical isomer? If you can remember, you draw the 3D structure and you draw the mirror image, then the mirror image will be its optical isomer. I'm not going to draw here, so let's consider that optical isomer as isomer number 3. Okay, then let's look at isomer number 4. Is there any chiral carbon? This carbon is bonded to H, but to same methyl groups, right? CH3, not a chiral center. This carbon is bonded to hydrogen, not a chiral center. Okay, there's no optical isomer. Number 5, isomer number 5. This C is bonded to 3 methyl groups. Okay, this C has only 3 groups of different atoms bond attached to it. No chiral center. Number 6, okay, no chiral center. Number 7, no chiral center. And number 8, no chiral center. Right, so altogether, okay, we have 1, 2, 3, 4, 5, 6, 7, 8 isomeric structure, okay, including structural and stereoisomerism. So the answer is D.